Hello, today I want to look at how you would find the area under a curve. And so, suppose you are tasked with find the area under a curve y equals 1/4 x squared plus 1 from 0 to 4. So this is a parabola that we've zoomed into. I want to know this area. And we're going to try and build our intuition with this. So if you were tasked with that problem, your first thought might be, well, what if I just count the squares under it? So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But then you're like, that 13 wasn't quite a full. I think all of those was a full one. That's 13. Maybe this is another one. That's 16 then total. Here's a full one, 17. These two together, 18. And you say there's 18 full squares. But then now the height of this is 1 and the width is 0.5. So those each have 0.5 square units. So you say 9 square units, final answer. But then you're like, I think I can do better than that because that was a little estimating, like this stuff here. Is that one full square? Well, I think I can do better. Plus it's a lot of counting. So you think, okay, what if I do some rectangles here with the same widths? So I go this one. Those two rectangles are good estimates. They each have a width of 0.5 and a height of 1. And then this one I think should go up to the height of 2. I'm trying to keep it somewhat easy, so I'm going to the nearest whole value. This one I think can go up to 3. This one I think, let's go another 3. And this final one should go all the way up to 4. So you look at the first two rectangles, they're the height of 1. This is then 2 times 1, 2 times 1, 3 times 1, 3 times 1, 3 times 1, and 4 times 1. So you've got 1, 2, 3, 4, 5, 6, 9, 12, 15, 19. But again, that horizontal width is actually 0.5, so I go times 0.5, 9.5 square units for the area. That's pretty good. But there must be a way to make these rectangles a little better because they're overlapping quite a bit. It made the calculations easier by going to this nearest full number on the y value, but it did throw off them. Okay, so now I want to make this way even better somehow. Well, the curve is what I'm trying to find the area under. So why don't I keep using these rectangles? Because, I like that idea of having the same width rectangles because it makes the calculations a little easier by multiplying by the same width. But this time, when I do my rectangles, I'm going to make the corner of it go up to the curve like this. So that defines my height. I keep drawing it so that left corner goes up to the curve. And we go like that. I like that. They're all underestimating it, but they're getting pretty close to the curve. But then they all have a different height to it. Each of them have this random kind of decimal height somewhere. Well, that one lands on 2, but like this one, is it 2.5, 2.6? What is it? Well, actually, let's think about what is it? What is this value? Or this one? Or this one? Well, it goes up to the curve. So this y value right here, or this one right here, it's at the curve's value. It is whatever the function equals at that point. You can almost call it f of x sub I. This one, f of x sub I. Well, that I is just notation because we're talking about the different x values that we're at here. And so if I want to be more specific, this one right here is at x equals 2.5. And so this value here is f of 2.5. That's its height. And what is its width? Well, we've been keeping it a steady change of x here of 0.5. And so to find the area of that rectangle, we would go 0.5 times f of 2.5. which in other words, that's your width times height, so the area of a rectangle. And we would have to go through that and do that for each of these rectangles, so all 8 of them. And we find that added up. And so it seems like that's a lot more work, but it does seem to get a nicer answer. In fact, we can use some good math notation to clean that up and make it not so bad as far as the math and all the writing. Well, at least eventually. Our first steps will have quite a bit of work to show, but eventually we clean that up with some formulas and things. Oh, and also, all of these underestimate it, but what if I drew those triangles a little bit different? In fact, this is the one I'm gonna work with really going forward. Is that time I drew my rectangles so that the left endpoint hit the curve. But what if I change this and I drew it so that the right endpoint hit it? So we go like this, and we're going to have the right endpoint hit it and down, right endpoint hit the curve and down. We're going to go this way. And what you're seeing with these curves, or these rectangles as I draw them, is they all overestimate the curve. If you think a step ahead, you're like, how do I find the best estimate? Maybe the average of these two methods, underestimate and the overestimate. And that's a technique, but we'll find a better way to get this better. Okay, so I have this, and I'm saying, how do I find the area of all these rectangles? Well, I drew them with a steady change of x equal to 0.5. So they each have a width of 0.5. It's the height that changes. And how do I determine the height? Well, I'm starting this interval at 0. And my first f of x over here, my first x value is 0.5 over. So you go 0 and then over 0.5. The next one is at 1, which is 2 times 0.5. The next x value is 3 times 0.5. The next one is 4 times 0.5. The next one is 5 times 0.5, and so on until I get 6 times 7 times, and this one is 8 times 0.5, which gives me the height of this is f of 4. Okay, so that gives me the x value. Okay, maybe we should back this up, and we'll see a pattern eventually here. How do I find the area of this first rectangle? Well, I'm going to go 0.5 times f of 0.5. Now the next rectangle, again, that is 0.5, but this time it's f of 1 because the height here goes to whatever the y value is at 1. Then we move over to the next one, the third rectangle here, and so again the width is 0.5, but this time it's f of 1.5. Go to the fourth one and we'll start seeing the pattern here. Again, the width is 0.5. We go to f of 2. You see how the f of value is increasing by 0.5 every time. It's increasing by that change of x. And we keep going until our very last one would be 0.5 times f of 4. You can see that this height is f of 4. I need to make this a little easier. That 0.5 is multiplying all of those, so why don't I factor that out? 0.5 times, well then it's just adding up all of the y values inside. Like this. And go all the way to f of 4. Okay, that's simplified a little bit. And hey, looking at that, that's adding up a string of numbers that have a certain sequence to them. This is starting to look like summation notation if we can work that into this. But to do that, I'm going to need to introduce more variables to this, more general notation. So we've already been calling that 0.5 the change of x. And so I'm going to go back to that, and we're going to say change of x is equal to 0.5. So then this becomes change of x times f of change of x times 1 plus f of change of x times 2 plus f of change of x times 3, and so on, plus f of change of x times 4. Because remember, that 4, that's 0.5 times 8. So I had change of x times 8 is what I meant to put there. This f of 1, it's change of x times 2. And so we can rewrite the formula in this way. If you remember summation notation, what you have with that is it's the change of x as I equals 1 up to some n value of your pattern here. And that pattern is going to involve an I, because that I is what changes each time you sum something. And you see how our value right here is counting up as if it's that I going through. And so I can write this notation as f of change of x times I times change of x. Now I put the change of x in the back there because that's a constant that is not being summed up, so we can take it all the way out of the notation, and I have this change of x sub I. And this little notation is summarizing what we did up there. And so for the full notation of finding the area of those rectangles, we could rewrite this as summation. Maybe we can get this a little better. Not great summation notations. What is our n? Well, that would be the number of rectangles, and it looks like we have 8 of them. So from I equals 1 to 8, we're going to put our change of x out here, which is 0.5. So I should write this, that our area is going to equal this, 0.5, and it's going to be f of 0.5 times I. And that's the summation right there for this problem. But wait, what is f of x? Well, we have that up here. F of x is 1/4 x squared plus 1. And so really what this is 0.5 times the summation from I equals 1 to 8 of 1/4 0.5 I squared plus 1. Now we could actually keep doing algebra on this, but we already see how, hey, I can now use some really good summation notation stuff on this. Because we have formulas. We have formulas for what the summation of I is, the summation of I squared, summation of I cubed. And so I can keep working with this. Let me let myself write it a little bigger here. The area is equaling 0.5 times the summation of 1/4 times 0.25 I squared plus 1. So that was distributing the square. So that is equal to 0.5 times the summation of, now I have 1/4 times 0.25, which is 1/4 times 1/4, so that's 1/16 I squared plus 1. And that would be 0.5 times, can take out that 1/16, so it's summation of I squared, and we can split up our summation. Now I have this, and at that point, you can put in the formula for I squared, and we can actually find this sum for us right now. Equals 0.5 times 1/16, and then the summation of I squared, well, also remember we are going up to 8, so in the formula, when we do the n, it'll be 8, so we go 8 times 8 plus 1 times 16 plus 1, that's 2 times n over 6, and that's our I squared formula if we forget it, and then plus 1 times 8. So I probably should have done this before writing that formula, but if we want to remember our formulas, I squared is equal to n times n plus 1 times 2n plus 1 over 6, and then the summation of a constant is equal to the constant times n. So n is your upper bound on those. Okay, so we have that. Now we're back to some algebra to try and simplify this. 0.5 times, let's see, we got this canceling and reducing down. So I have just left with 9 times 17 over 6 plus 8. And we got 0.5 times, that goes to a 3 and a 2. So I have 3 times 17, which is 51 over 2 plus 16 over 2. And now we got 1/2, changing that 0.5 to 1/2. Add my fractions, that's 67 over 2, which is 67 over 4, which is 16.75 units squared. And so with that, we get that estimate of 16.75 units squared, and that's provided I didn't make a mistake in simplifying. But anyways, we're like, I think I could still, that's still an estimate on what I'm doing. And so then you ask yourself, I did this pretty good by that summation notation. I like what I did. I like how I figured out this sort of general formula right here for the summation of the rectangles, which helps find me the area under a curve. But I'm like, I think I could do better because it's still an estimate. And so this is where, with the calculus starting to come in, we ask ourselves, well, wouldn't this estimate be better if I made these rectangles smaller? So over here, instead of drawing them that big, maybe like this big, because then as they go up to the curve, they're missing less, so maybe a width of 0.25, which would mean we draw 16 triangles, not drawing them perfect. But you do start seeing, oh yeah, that leaves less space under the curve. And then your calculus brains start really thinking, and you say, well, why stop at 16? Why not do 32? So I'm making them a width of 0.125. You say, hey, that's getting really good. And you jump right to, well, why should I draw a certain number when I can do infinity? Yes, if you can let those rectangles go to infinity, have an infinite number, that would give you the perfect curve. And so in our formula here, it's all the same thing, except we say let the limit as n goes to infinity of that whole expression. So now the number of rectangles are not just 8, not just 16, 32, but an infinite. And so what that would mean is you keep doing the same thing, but at this point where we actually plugged in an 8, because we had 8 rectangles, our n was 8, we would just plug in an n, and then we would have the limit. Now this is a little messy because this is for another video, for another time, the next step of it. But you'd say the limit as n goes to infinity of that, and you would evaluate your limit, and you would get an exact answer for the area under the curve, the area under this one. And that's kind of how we build a calculus intuitive understanding of how we're going to be finding the area of the curve. And that's the limit definition of it. So it's pretty messy, it's pretty long, a lot of summation work. And that, of course, will get simplified with some formulas and go quicker eventually.